Throughout Earth's history, there have been many mass extinctions. For example, the one that took out our friend the trilobite here. But what causes these extinctions? In this video, I'm going to be talking about the top 3 causes of mass extinctions. There have been so many mass extinctions through Earth's history, and this list on the screen right now is just to name the most severe mass extinctions, or at least the most severe known to date. These run from all the way back to 2.4 billion years ago to 65 million years ago, when an impact caused the extinction of the non-avian dinosaurs. But extinctions didn't stop at 65 million years ago. That's just the last time that they were super severe. They've continued throughout the Cenozoic era from 65 million years ago to today. And I talk about all of the events on the screen here, as well as other climate change and small extinction events throughout the Cenozoic and other videos. I will link one up to the top right where I go over most of these, but I'll link more down below in the description box if you want to check those out. But there hasn't just been one single cause for all of these extinction events. They've all been caused by a different combination of factors that came together to create really devastating conditions. But there are 3 common factors throughout most, if not all, of these extinction events, and these seem to cause the most actual extinctions of life throughout these events. These include anoxia, or the lack or depletion of oxygen in most typically the ocean, but can also occur in the atmosphere and cause devastation to land life as well as marine life. Elevated CO2 and associated acidification of both the ocean as well as acid rain, soils, etc., and global warming. These are the 3 factors that occur most commonly in association with mass extinctions and likely cause the most deaths that lead to the actual extinction event among life. And these are what we'll talk about throughout the rest of the video, but before we move to that, I just want to mention that there are many other factors that contribute to mass extinctions, just probably not at the magnitude that these other 3 do. These other factors include toxic metals like hydrogen sulfide and mercury, which tend to spike during extinction events, the blocking of sunlight due to either volcanic ash or dust that's blown into the atmosphere after an impact. This blocking of sunlight not only causes a rapid cooling trend, but also leads to a lack of photosynthesis. And then there's also direct effects of impacts in volcanic eruptions like tsunamis, blast damage from impacts, lava flows from volcanoes, earthquakes, and wildfires. Ozone destruction is another common one, which increases UV radiation. The reason ozone is susceptible to breakdown during such extinction and climate change events is because typically the gases released from either impact or volcanic activity can break down the ozone. And then finally, astronomical effects such as nearby supernovae that might cause gamma radiation to reach Earth and cause destruction that way. But again, these are all just kind of side effects that either contribute in a minor way to a lot of extinction events or in a major way, but only to a few extinction events through Earth's history. The 3 top ones, again, are anoxia, elevated CO2 and acidification, and global warming. But what causes these things to occur? These actual kill mechanisms that directly cause the extinctions, what causes these to actually be set off or increased during the time that the extinction occurs or just before? Well, the triggers for mass extinctions are different than the actual causes of the extinctions. The triggers of these climate changes start with typically volcanism, most often the emplacement of large igneous provinces, which can cause super widespread and long-term volcanism in a certain region of Earth that releases all sorts of gas to the atmosphere that causes these effects. The other major trigger, though, is impacts. Impacts can have very similar dust and gas releasing effects as large igneous province eruptions. And we saw this happen at the KPG, or Cretaceous-Paleogene boundary, with the dinosaur extinction event. The correlation between volcanism and extinction events through time is pretty well established. There are many extinction events that are associated with LIPs, or large igneous provinces, as shown on this map. These are some of the large igneous provinces that have been emplaced through Earth's history. The Frasnian-Flaminian, or late Devonian mass extinction, is associated with the Vilui traps. I'm sorry if I'm pronouncing it wrong. The Capitanian or Guadalupian extinction event near the end end of the Permian just before the very big end Permian event, the Great Dying, is associated with the Emetian flood basalts, and the end Permian Great Dying event is associated with the Siberian traps. The end Triassic event is associated with the Camp volcanism, or the Central Atlantic Magmatic Province volcanism, and the Tortian Ocean Anoxic event and associated mass extinctions is associated with the Karoo and Barra traps. However, many large igneous province events are not associated with mass extinctions, so we still don't know all the factors that determine the lethality of large igneous province eruptions. However, the temporal link or correlation between impacts and mass extinctions is even less well-founded than volcanism. The only real convincing example of when an impact led to a mass extinction event, or at least correlated with one, is the end Cretaceous event, like I mentioned with the dinosaurs. The Chicxulub crater is one of many craters and impact events through Earth's history that have been identified as of yet, but again, it's the only example in which a mass extinction seemed to have directly resulted, or indirectly, but sort of kind of directly resulted from that impact. In any case, it's still clear that the two major triggers that actually cause the climate changes that cause the extinctions are large igneous province eruptions and impacts. So in this video, we'll talk about these three kill mechanisms during mass extinctions, or three major ones, and that is global warming. We'll talk about what causes it and what effects it has on life. Then we'll talk about the same thing regarding CO2 increase in acidification, and then we'll go into anoxia. Large igneous province eruptions release enormous amounts of CO2 to the atmosphere. This is a greenhouse gas, as we all know, with a long residence time, meaning it stays in the atmosphere without breaking down for long geologic timescales. And CO2, because of this reason, can cause significant global warming over geologic time. Many other harmful gases also contribute to mass extinctions upon release from volcanoes during large igneous province eruptions. However, they don't seem to cause as many deaths as CO2 and global warming directly, so we'll talk about those in a separate video I'm going to do over the other causes of extinctions, which I'm going to call Extinction Causes Nobody Talks About. So check that out whenever it's out. It should come out not too long after this video. A single volcanic eruption is unlikely to cause significant CO2 rise, but repeated, closely spaced large igneous province eruptions can induce global warming. As you saw on the map shown previously of large igneous provinces, they cover immense regions of Earth's land. And as I talked about in my Great Dying video, some of these large igneous province eruptions went on for millions, yes, millions of years, a couple million years. So that is how large and repeated and long in terms of duration these things have to be to really cause significant events. Additionally, the baking of organic rich sediments as magma rises through Earth's crust can greatly exacerbate the carbon release and warming. The burning of this previously deposited organic carbon increases the amount of carbon that is oxidized and released upon volcanic eruption, both in the form of CO2 and methane, which are both potent greenhouse gases. This baking of organic rich sediment would account for major negative carbon isotope excursions at the time of large igneous province eruptions. Carbon isotopes are a great measure of when large releases of carbon due to volcanism or impact or other reasons have occurred in Earth's past. The reason that carbon isotopes are great for this is because photosynthesizing organisms that eventually make the organic carbon deposits in the rock record preferentially take up light carbon, making a really negative carbon isotope signature in the rocks. And when they do so and then die and then settle and then become buried as organic carbon sediment, this causes a really positive isotope excursion in all the other carbon-containing rocks, like carbonates, for example. However, when we look at carbonates during times of great organic carbon oxidation and release, they have a really negative carbon isotope signature because all of that organic carbon is giving back its light or negative carbon isotopes to be preserved in other carbon-containing rocks like carbonates. If that doesn't make sense, I talk about why carbon isotopes can help us reconstruct these things way more in other videos, including my stable versus radioactive isotope one. I'll link it to the top right for you if you want to check it out. There's direct evidence for coal combustion in the sediments from the end Permian extinction, for example. And there's also evidence that high temperature reaction with evaporite generated halogen gases as well, which might have caused additional damage because it caused ozone collapse, or at least partial ozone collapse. Halogen gases are things like chlorine, fluorine that can form hydrochloric acid, hydrofluoric acid, which can contribute to acid rain, as well as the destruction of ozone. And I will talk more about this again in my other extinction causes video whenever it's out. But just keep in mind that the carbon release is just one thing that the volcanoes and impacts or whatever are doing when they're burning this old sediment and releasing all these gases. Methane also contributes to warming. Global warming itself leads to the melting of frozen methane hydrates in both terrestrial and marine sediment, and this release of methane amplifies global warming, causing more melting of the methane, and so on and so on. This is a positive feedback loop, something that is caused by the warming that causes more warming. Another example of a positive feedback loop is with ice and albedo. The more warming there is, the more ice that melts and the less solar radiation is reflected from the light surfaces on Earth, and the more that's absorbed. This causes more warming and more melting. Thankfully on Earth, there are balancing effects or negative feedback loops that kind of balance out these positive feedback loops, or else we'd get runaway greenhouse or ice house climate change anytime anything fluctuated slightly. However, rapid methane hydrate melting has been shown to cause major and rapid warming spikes during certain extinctions in the past, and that has clearly exacerbated these extinction events. This effect has been implicated in the end Permian and in Triassic mass extinctions, as well as the PETM, or Paleocene-Eocene thermal maximum, as well as during the warming since the last ice age just recently. Although methane is a more potent greenhouse gas than carbon dioxide, it thankfully has a shorter residence time in the atmosphere, meaning relatively quickly on geologic timescales, it breaks down and it's no longer in the atmosphere, causing that really intense greenhouse effect. However, what it breaks down to is carbon dioxide. So it's not that great because it doesn't just disappear. It breaks down into carbon dioxide, which, as we all know, is another greenhouse gas. Even though it's less potent, it lasts longer and causes sustained warming over geologic time. So what kind of effects does global warming at this scale during mass extinction events have on life, and how does it directly cause extinctions of life? When temperature changes on land or in the ocean, geographical ranges of species typically change in response. In other words, they migrate. They migrate equatorwards during cooling and polewards during warming. But not all species can migrate. So what happens when a species can't migrate, or the rate of change exceeds its rate of migration, or there's just no suitable habitat that remains for it to migrate to? Many organisms and animals respond differently to warming rather than just migrating to somewhere more favorable. One common response in animals is increased aerobic metabolism. Maintaining a higher metabolic rate requires more oxygen, so their oxygen demand goes up with global warming, as well as global cooling. And active organisms can elevate their metabolic rate during bursts of activity and have a higher aerobic scope compared to less active organisms. And this agrees with evidence from previous mass extinction events that shows that active organisms were more likely to survive. However, different populations of the same species have even been shown to vary in their response to temperature, making it so hard to understand how exactly things respond to temperature and why exactly global warming and temperature change causes extinctions. Typically, species that vary in their response to temperature have populations that live in more variable climates, which typically can adapt more easily compared to those that live in more temperate climates that can't adapt quite as easily to temperature change. And other effects that warming causes that we likely wouldn't even know about if it wasn't for current global warming, so we can look at modern animals rather than just fossil record, is, for example, coral bleaching. Coral bleaching is a process in which the symbiotic algae, the zooxanthellae, within corals escape in high temperatures because it's unfavorable, and this leaves the coral to die. The coral can recover if the algae come back in time, but it typically doesn't because the temperature doesn't typically go back down. This is different than ocean acidification, which also causes stress on corals and other calcium carbonate secreting organisms by basically dissolving them, because acidification leads to dissolution, but this is different. This process of bleaching is temperature driven, not acid driven. So corals are under two major stresses right now, one being bleaching due to temperature stress and one being dissolution due to acidification. Another effect of temperature on life we probably wouldn't know about if it wasn't for modern life and modern warming is the effect on reproduction cycles and sex ratios. For example, sea turtles have been shown to have temperature-dependent sex ratios in their nests, where the female to male ratios increase with an increase in temperature and decrease with a decrease in temperature. There's a happy medium in there where they get both females and males in their nests, but if they're not at that happy medium, they will skew to one way or the other, making it difficult for populations to maintain reproductive ability. Now, I want to mention really quickly before we move on to the next stress, which is CO2 increase and acidification, that cooling has also been shown to cause mass extinctions, for example, the end Ordovician or the Mississippian Pennsylvanian. Rapid global cooling or global warming is not good for ecosystems. I mean, any rapid temperature or environmental or climatic change is not great for ecosystems that have evolved to the current environmental conditions. But existing evidence cannot yet confirm whether temperature stress, either warming or cooling, affects life globally and more drastically than other stresses, or if other stresses that accompany such temperature change do more damage. One such temperature-associated change is, for example, ocean acidification. Increased CO2 concentrations during periods of large igneous province eruptions and/or impacts that impact carbonaceous sediment and release a bunch of carbon dioxide to the atmosphere can also cause ocean acidification in addition to warming. Ongoing large igneous province eruptions can generate significant ocean acidification, especially if they're continually pumping out CO2 for long periods, long durations, like the 2 million year one we talked about earlier. Evidence for ocean acidification during the end Permian extinction is found across the northern margin of Pangaea, or what was Pangaea, where carbonates were basically eradicated from even shallow waters. Right now, the modern ocean chemistry is such that the deeper waters is where carbonate minerals can dissolve because the acidification and CO2 saturation of waters increases with depth in cooler, deeper waters. But in shallow, warm, sunlit waters, carbonates can precipitate happily, forming large reef ecosystems. However, during periods when CO2 increases greatly, the acidification depth, or depth where carbonates will dissolve, rises in the ocean and sometimes has even spread to very shallow depths, really wiping out coral, sponge, mollusks, and any carbonate-secreting ecosystems. The reason acidification has such a large effect on carbonate-secreting life is because it lowers the available carbonate concentrations in the water, which makes it really difficult for organisms to produce their carbonate skeletons. There are organisms that can buffer against CO2 changes and survive acidification events. This is a physiological process that prevents drastic changes in an organism's hydrogen ion concentration. If you don't know, pH is just a measure of hydrogen ion concentration. And some organisms can use weak acids within their bodily functions that take up or release hydrogen ions as needed to buffer against CO2 and therefore pH changes. But what happens when organisms cannot buffer against increased acidity? Well, the short answer is just that they die, unfortunately, and sometimes so many of them die, they cannot recover and they go extinct. Among the most heavily affected during periods of acidification are the carbonate secretors. Anything that secretes carbonate skeletons is greatly affected by acidification, especially those that can't buffer against such changes. But acidification can also directly affect fish behavior by impairing olfactory discrimination and neurotransmitter function. Acidification also alters peptide signaling molecules, preventing organisms from detecting predators and staying safe from predators, as well as detecting potential mates, and that reduces reproduction capacity. However, acidification is not the only effect of carbon dioxide increase. Hypercapnia is a condition in which CO2 becomes elevated in your blood, and that can be fatal. This can happen to any animal life because too much CO2, what we breathe out, is not good for us. We want oxygen, not CO2. Hypercapnia is typically more severe for marine life because CO2 is 28 times more soluble in water than oxygen. And as I'll show later, oxygen actually decreases solubility during global warming events, which is typically coinciding with carbon dioxide increases. So oxygen availability is decreasing for the animals while CO2 is increasing, and that causes severe hypercapnia and therefore deaths among marine life. Terrestrial vertebrates are not out of the woods, though. They might also be susceptible to hypercapnia under very high atmospheric carbon dioxide periods. In modern animals, growth rates, reproduction, and survival have shown decreases upon exposure to atmospheric carbon dioxide that's just 200 parts per million above ambient levels. And experiments showed that organisms suffer from both hypercapnia and reduced biomineralization potential when carbon dioxide is increased and pH is decreased. Again, this is what we talked about earlier. The hypercapnia is just the direct increase in CO2 in blood, and reduced biomineralization potential is the effect of acidification on organisms that biomineralize or produce skeletons or hard parts. Hypercapnia has been implicated in the end Permian mass extinction as well as the prolonged recovery during the Triassic, the period just after the Permian. Principal extinction victims during this time were those that secrete carbonate skeletons and or have a limited capacity to buffer against decreasing carbonate. And this is consistent with both an ocean acidification and hypercapnic stress effect. But warming and CO2 increase not only cause hypercapnia and acidification, but also reduce oxygen solubility, like I mentioned earlier, and that can cause anoxia. Anoxia is the lack of oxygen. Typically, when we say anoxia, we're talking about ocean anoxia specifically, but in some cases in Earth's history, there have been slight decreases even in atmospheric oxygen. So it can affect marine life heavily and sometimes even terrestrial life. And it's not only caused by decrease in oxygen solubility during warming, but also ocean circulation changes associated with weaker temperature gradients from pole to equator. This just means that when temperature gradients are weak from pole to equator, in other words, there's not ice at the poles and it's melting, and the temperature difference isn't as great, that's when ocean circulation becomes weaker because this temperature gradient is what drives ocean circulation because it's thermohaline circulation. It's driven by temperature and salt content. So when ocean waters circulate to the poles, the surface waters become cool and they sink to the bottom and they drive this belt of thermohaline circulation. But when they're too warm to sink, they stop driving ocean circulation, they stop driving ocean mixing, and the ocean becomes more stagnant. Ocean stagnation can greatly increase ocean anoxia because it typically occurs in the deeper ocean, and when there's no mixing between deep and surface water ocean, you're not going to get the mixing of oxygen into those deeper waters, and the anoxia just spreads. It also is caused by increased primary productivity during periods of increased CO2. Increased CO2 drives primary productivity or photosynthetic blooms at the ocean surface because they take up CO2, release oxygen. And beneath these blooms comes a flurry of aerobic organisms that use up all the oxygen to oxidize that organic carbon that the bloom is producing. And then below that flurry, the oxygen is all used up and the deep ocean becomes anoxic. Then the ocean circulation changes cause ocean stagnation, which allows the spread of this anoxia throughout the entire ocean, and it can become a global issue. So what are the effects of anoxia on life? Well, warming, like we mentioned earlier, already creates greater oxygen demands in animals. And when you have further oxygen depletion, it can be incredibly lethal. However, it's important to note that Anoxia would have had to spread globally to be the sole killer in many of the past extinction events. Even during the Permian, where we have the most complete record of Anoxia, the timing, magnitude, and extent of Anoxia varied across different environments. So Anoxia likely acted among other stress mechanisms to induce widespread devastation. But if you want to hear more about the actual mass extinction events and kind of the major effects they had on life and the groups that were affected, you can check out my other mass extinction videos. I will link the Great Dying one up here because that one is the greatest mass extinction of all time. And I'll also link the Moss extinction event one, which is the Ordovician one, when moss might have been the initial trigger to all of this. And so you can check these two videos out if you're interested. And with that, guys, as always, my references are linked in my description box below, and I can't wait to see you guys in the next one. Bye.